Okay, in number 20 here, we've got g, which is a twice differentiable, meaning the first and second derivatives exist, a twice differentiable, but increasing function of t. And they've given you two values here, guys. G of 0 is 20, and then g of 10 is all the way up here at 200. So we've got a function that begins somewhere right about here at 20, and it looks like it ends at the ordered pair 10 and then 220. So I'm just going to randomly say, okay, the point 10, 220 is right about here, and g is a function that needs to connect those 2 points. Now, they did tell us that the function is strictly increasing right here, so I can't draw something that goes up and then comes back down again, because that function would not be increasing for all values of g. So I've got to connect these 2 points, and probably the most boring way I could do it would be as a linear function connecting the two of them. Okay, I could just draw a line that looks like this, but we know it's also possible here that there's some concavity to this curve. So it could be increasing at an increasing rate like this. It could be increasing at a decreasing rate like this. And then maybe the most interesting case here, guys, is that it could have a change in concavity even though the function is increasing. It could be one that increases slowly at first, then picks up and starts to increase fast in the middle and then more slow again. So there might actually be a point of inflection right there in the middle. So I've kind of drawn 4 different possibilities for how we could get from point A here to point B that all kind of satisfy the little bit that they told us about the function. The second derivative always exists, which means the first one does as well, and it's strictly increasing. So which of the following must be true? Meaning in all possible cases, it definitely has to work out. Well, how about A? G prime of t is equal to 0 for some t in that interval? Well, guys, that's one we have to throw out right away. They told you the function was increasing on that whole interval right there, and so to have a tangent line that has to equal 0 could happen, but there's certainly no guarantee that it does. And in fact, I've drawn, I think all 4 cases right there that show a function that doesn't have a horizontal tangent line. So for A to be the answer, that would have to happen all the time, and that's definitely not the case. Now B, g prime of t, the value of our derivative, would have to equal 20. As I looked at somewhere in the interval, as I looked at this problem, I had a feeling that might be the right answer. What we very often do, guys, is we talk about our old buddy, the mean value theorem, which would say something like g prime of, and there'd be some c value right there, would equal, and it would be g of b, your right endpoint, which in this case would be 10, minus g of a, 0, all over 10 minus 0. So let's think about that. G of 10 is 220 minus g of 0, which is 20, all over 10 minus 0. Gotcha. And that numerator then becomes 200, and 200 divided by 10 is going to be 20. Now, if this function satisfies the hypothesis of the mean value theorem, that means that there's got to be some value of c in between 0 and 20 for which the slope of the tangent, or the derivative here itself, has to equal 20. And what is the hypothesis here of the mean value theorem? A function right here would have to be continuous and differentiable everywhere in between, and that's what we know here by saying this function is twice differentiable. So B is going to be our answer. Now, real quickly, why not C or D? C says that your second derivative would have to equal 0 for some t in the interval. The graph that I drew in red has that happening, guys. Your second derivative is equal to 0 at that spot right there. Also, in the linear case that I drew, the second derivative would be 0 the whole time. But in this top case and in this bottom case, the second derivative is equal to something other than 0 for the entire stretch right there. So we'd have to throw out C. Okay? And then for D, the second derivative has to be positive for all t in the interval. Well, this curve right here supports that idea of a positive second derivative, but this curve up here on top refutes it. That's one I drew there, a function that was increasing at a decreasing rate where the second derivative is negative the entire time. So we'd have to throw out D as well, and that just reaffirms our belief right here that our answer for 20 is B.